Yesterday, Professor Kundalwal and I myself actually was telling that this is a daughter of graphite. Graphite is an insulator, but graphene is semi-metal, right? Yesterday I was telling what is called semi-metal, and it has a Dirac cone, and we did not only single layer graphene, we did also two layer graphene. How the graphene is working in battery, which is one of the promising material for battery, and how the charge particle is moving inside the graphene. We also did such kind of work. You may find out such kind of work, how the metal ions can move inside the graphene, and when they're moving, how the electronic properties and how the change is happening. Hmm. Of course, we did the pure graphene. Might be some defect can change, can enhance such kind of properties. So we are working on not graphene, some other 2D materials which have defect, using such kind of analysis, using density functional and molecular dynamic simulations. So in another cases we'll see this called 2D materials, which is basically transition metal dichalcognize, which is basically MOS2 I did. Then I did not only that, MOP we did, or is doped MOP. This is called chalcogen. Two-dimensional chalcogen materials, 2D materials. And WX MOX 1 minus 6, which is called TMD's alloys. What is W? W is basically tungsten, and MO is basically molybdenum, S is the sulfur. So in that cases, we did nice work in 2019, 2017. We published one of the nice article, and after 2 years, in just last year, probably around middle of that last 1 year back, we published transition metal phosphide and sulfur doped in acid catalyst. Then we work on these covalent organic framework as semiconductors, and recently we already work on that probably 2 years back. It's going to be published soon. I don't know exactly when it will be published, but it will be published soon. This work I did using just simple density functions theory in 2017, and you can see that journal quality is also very important. JPCC, JCP, ACS Nano, JPC, these are very good journals in our material science and engineering. Then metal organic framework I worked, that I told, to develop such kind of force field parameter. It was not easy today when I was discussing the force field parameter part little bit. In that cases we did the work in metal organic framework just to development the parameters, and how this how this linker, how this kind of structure is behaving, or how this linker is rotating around this axis. It will be very difficult, it's not easy task, so we did couple of work on that. Then we just completed one work using the 3D covalent organic framework. When we have added some kind of simulation, what happened, a lot of hydrogen has been stored inside the cavity, and we got hydrogen storage, which is the target. And I'm writing on that particular article. In these cases, two things we did. First is the molecular modeling we did. We have estimated the enthalpy, and then we did the grand canonical Monte Carlo simulation and classical molecular dynamics simulation and kinetic Monte Carlo simulation. Using simulation, it is a snapshot of the simulations, lots of hydrogen where they are capturing. In these cases, we also studied that thing. So in these cases, we did also experiment and MOS2, how this experiment is working, we'll see later on. And we also did one work on zinc air battery, and where we have used instead of graphene. I was saying that graphene is very good for battery. Instead of graphene, we are using the carbon nanotube and nitrogen doped carbon nanotube. Okay, and you can see that journal quality is advanced energy material, and that is the till now this is the best catalyst, and this is the best material for battery. Carbon nitrogen doped carbon nanotube also, it was published in advanced energy material. In advanced energy material is one of the powerful journal in energy science. The impact factor of the journal was around 25, and this is the SCS nano above around 14.6 is the impact factor. So these are the not easy work from our side also. And reviewer also, it is so hard. They are also checking each and every line. He is going to check what we did. So such kind of work using simulations, atomistic simulations, and density functions theory, we did that. Uh, so let's see other project also we did. It is called oxygen reduction catalyst. Okay, what we did, we have defined some material. If you look at very nice here, this is basically gold, right? And what happened, we actually on the top of the gold we put the graphene. If you look at So previous slide, the graphene looks like not distorted. Okay, if you look at in this work, we found that the graphene was distorted. We know why. The gold is interacting the graphene. So that's why this is not like a straight plane. Okay, and we found that this case is what happened. The oxygen had been reduced by that kind of 2D materials. Okay, this is 2D materials. All are 2D. And when we put on the top of the graphene, it is called one of these chemical, name is phosphorin or something, catalyst. What happened? This catalyst, iron-based phosphorin catalyst, it will work for a catalyze this reaction, what called O2 reduction reaction. If you remove this, what happened? The interesting thing in the experiment, look at. If we remove the graphene, the activity of the material is decreasing. If we insert the graphene, the activity is increasing. Okay, it was very interesting topic in that time. We are able to publish this in 2018 in again IISER Nano. It's one of the powerful journal for that. So we have experiment and theory, and we studied this kind of behavior, CV characteristics we have performed in analysis. Then also we work on the thermoelectric materials. In 2019 we published thermoelectric and electronic properties of the covalent organic framework, and also on HPCC. Then we work also the novel battery design. It's called potassium ion battery and co-intercalated battery, lithium ion. So this is the in my left figure, the the green small ball is the lithium and purple ball is the potassium. So we showed that. So you know the reality, the problem is if we are using too much lithium, so everyday lithium is decreasing. So we have to replace lithium by some other kind of ions. So we found that probably potassium is the one of the promising for that. This one of the promising material for that, which could be replaced by the lithium could be replaced by the potassium. And also we tried for sodium, that we are also working on, and our some student, his name is Akash, will work on that. He has to focus on how this kind of battery will work, the integration. And this is the picture of that. In this case, his battery has, these are the graphene, basically graphene, many layer graphene, and between two graphene layer the this kind of integration there. And here you intentionally I didn't put any layers, just I didn't put, you may put some, let's say another potassium. Okay, this is called the how the ions are intercalating or passing through the graphene. And this is the picture of the in experimental graphic. So these are the solid electrolyte interface, which is lithium based, and the blue color here represents my potassium ion, and this is the purple color here, and lithium is the lithium is this. But here if you look at it, randomly they intercalated. Okay, but we try to intercalate only one kind of system, one kind of ion in between two graphene layer. If we add, what happen if we add randomly, the symmetry will break. That is the problem. Okay, so symmetry will break mean what happened, our calculation will take long time and competition will increase. So we did like this way, whatever it is we have to fix the concentration, because the battery performance will depends on the concentration. And we are happy to say that this article has been published in Journal of American Chemical Society in 2018, both experiment and theory. In that cases we did the Raman effect, Raman shift, Raman study we did in experiment, I did, and synthesis of this material also we did, and theoretical study also I did. And all our students, our collaborator also did perform the experiments of how to synthesize this thing. So this is the way we did. And then we also work on the field effect transistor, okay, which is very good transistor, the bipolar junction transistor. So in that cases we replace this silicon germanium, whatever I was teaching probably a couple of days. We throw that kind of silicon germanium, we use arsenic doped black phosphorus. This is one of the promising material for field effect transistor. There are couple of material and couple of layer we have done, and I am happy to tell with our collaborator we are published in experimentally this field effect transistor has been synthesized in the lab. And finally we are able to publish such kind of article in ACS catalysis. Okay, so in that cases what happened, so we observed that how the material behaves, and how this kind of how the system of to the system, how it works for the field effect transistor. Such kind of analysis we did. So this is the way I tried to I tried to explain both theory and experiment at the same time. That's why the we are able to go to a big journal. So so this is the way. Let's see how another work we did. And recently we worked on just couple of months back, hydrogen storage in covalent organic framework, and that article also published in JPCC. And the BJT bipolar junction transistor using arsenic dope black phosphorus was able to publish in nanoscale journal. Mm. This is also very good good article. Also, if you want, I can share with the article. But these are the research topic we are working on that. So, so I can give some outline of that kind of research work we did. Which one is the first one is the basically related to physics and material physics related area. Then you can potassium intercalation also there, and TMDs also work will be there, and many others also we will teach. Let me explain what we did in that particular work, which is very important. I know that everyone should attend, but many of us didn't attend. I don't know why, but they should learn if they really want to take this course and the development of their program. So first one is called Dirac cone in 2D material, 2D bilayer graphene by intercalation of transition metal. Second case is we will see the achieving fast and efficient potassium intercalation on ultra thin graphene based electrode, which is modified by a lithium based solid electrolyte interface. Third one will replace the theoretical and experimental study of 2D layers transition metal like recognized, for example, MOS2, WS2, and their hybrid materials WXMO1 minus S2 and their potential applications for hydrogen evolution reaction. And let's see how it works. Again, I will repeat that thing. This is the first scanning microscope structure of the graphene. Okay? It is called honeycomb structure, and these are basically the atoms and these orbitals. They first AKGM observed. AKGM and also they are the potential kind of formula. I will see that. And they also observed when the graphene it has a very good symmetry, the layer symmetry P6 mm, and they were successfully synthesized in 2003 and single layer. It was a big challenging for probably 100-year question that how to synthesize monolayer graphene. AKGM and Nossolov first time synthesis, and their article was published in Nature in that time in 2003. They showed that they synthesize, and they also studied that it has a Dirac cone. If we plot the band structure in K yesterday I was discussing, it looks like the band. This is the conduction band, this is the valence band. You will see that at K point here, here, maybe others many places, it form a cone, like a cone. In that cone, what happened is the bands are just exactly touching the Fermi surface and form 3D cone. This cone is called Dirac cone. So we started that Dirac cone yesterday I was discussing. This is the way we did. This is the Dirac cone part. We what we did using the density functions theory, we explore all these things. Okay, whatever today discuss or yesterday discuss using that such kind of method, we are able to really explore such kind of band structure, density of states. The right this figure is the band structure. So when we are plotting the band, there are many questions. Okay, when 2D material, there should be some reference. Okay. So the band energy, the electronic band energy, we plotted with respect to the respect to vacuum. And in this cases, when we'll work on the materials, quantum matter nanoscience, always the energy we need will be electron volt. Fine. When we'll study the not electronic energy, that electronic will be new unit. It is called Hart tree. Okay. So you look at the band energy we plotted with respect to vacuum. In y-axis it is represented, and these are the bands I have plotted. High symmetric MK gamma M direction. And this is the symmetric K vector. What I can give different name. There are many ways to give the name, but I plotted MK gamma M direction. And total density of state I plotted. Heat is the total density of state for these cases. You will see that exactly at Fermi. This is the dotted line represent the Fermi. Where is the Dirac cone had formed or Dirac point? I circle it is. If it is a cone like 3D structure, I said this is the cone. This is the basically cone here. What we observed exactly at the Fermi level, there is no electron density. The total density is 0 here. That is basically at the Fermi level 0. If we cross the Fermi, because there are lots of bands are here, the electron density or the probability of finding the electron is there. Okay, and we are Nowadays, with the sophisticated calculation, we can calculate the form where the electron density is coming. We know the carbon atom. Carbon has sp orbitals. When graphene has been formed, it has sp2 hybridized. And when we studied the SPD analysis, if it's go to higher state, that's why D, we today learn now when for neon atom if we go to phi 1, so we found that no, there is no electron density when we have the D. That is the blue almost zero, maybe higher excited state possible there are some electron density. But in P, if you look at, most of the electron density is coming from the only P. So that's why total density, whatever the trace or locus, is coming only the P subcell, not even also S. S is already created the covalent bond, and they are not free, it is the semiconductor characters. So, and then we also explore P has three component, Px, Py, Pz. That is the subcell of the P orbitals. Okay. So, and we also did analysis from the Px, Py, which orbital is required for that. We found that Px, Py are not taking part in anything. Only the Pz, and Pz subcell electron is the providing the electron density, and that is the most. That is the reason. That's why the material is working for the Dirac. So PZ subcell if there, then possibility is there, and also many things, many parameters required. Today we'll discuss why the Dirac for there, because the mostly the configuration is that the symmetry, the structure is very much important, as well as the orbital cell electron to have the Dirac cone. We have the conclusion soon. And another outline, I also describe the how the 2D material can go up. We will also describe the A-stoped monolayer material, which is high efficiency of electrohydrogen evolution reaction. We will also show that theoretical and experimental study of the genus TMDs, or sorry, transition metal chalcochronides, which is MOS2 WS10 hybrid material, and their application in hydrogen evolution reaction. Will show the how the zinc air battery is working, which is catalytic activity for end of carbon nanotube, which is the area of rechargeable zinc air battery. So, and this is the one of the snapshot of our 2D MOS2 structure. In the graphene, this is the graphene structure. Actually, what happened after the development of graphene in 2003, a 2D material, such kind of 2D material like mixing other HB and hexagonal boron. Right now, I'm working on that. Graphene, black phosphorus. I already did the work. Did you see the black phosphorus for field effect transistor? This is the structure of black phosphorus. But we did the arsenic black phosphorus, multi-layer graphene, transition metal dichalcochronides. This is the MOS2. Then this is called hexagonal boron nitride. Then many others also, for example, intercalation between two these, let's say iron chloride, or ferric chloride, or aluminum fluoride may be intercalated between two, that for aluminum ion battery. Mixing also there. After the development of the graphene, that's why it is my circle. 2D material like explode like a bomb burst, explosive. So exponential population growth are rapidly growing for social issues as for the global energy demand. Maybe that after 50 years there should not be any kind of petrol, diesel like that way we are using today. So if we lose all these things, we have to finding some alternative. Another thing is that we have to find out the green energy sources, because when you are burning petrol, diesel, coal, what happened? Lots of carbon dioxide, carbon, and greenhouse gases are entering our environment, and lots of effect is there. So basically what happened, the global energy demand intensifies our reliance on dueling fossil fuel reserve with the unprecedented environment consequence, which is very difficult and unprecedented to be one of the challenging tasks to overcome this thing. So let's see what again I'm trying to go through. Dirac cone in 2D bilayer graphene by intercalation of transition metals. And why transition? You will may ask, why transition metals? Why not others? Of course, you can do. I did only for the first this only graphene and then transition metal. Later on, we are working on the alkali ion, some battery purposes. Also, I also did alkali ion. In near future, of course, I will also show alkali ion in maybe other course and other lectures. So what happened? What is the definition of graphene? If we ask, many guys will say in opposite, and this is the basically scanning my microscope image, whatever SCM we say, na? Scanning is this scanning probe PMC like image graphene we observed in 2004, 2003 and 2004 this time actually. Andrew James and Konstantin Nossolov developed such kind of graphene in the University of Manchester in the Department of Physics. Okay. And they was informed that the existence of theoretical description and composition, structure, and property, it was theoretically described at the same time. So what is the definition of graphene? Graphene basically is a 2D honeycomb sheet of carbon, just one atom thick, where all this kind of a carbon when create the bond, for example, this carbon to this carbon create a bond, it is, and the orbitals are sp2 hybridized bonded orbitals between the carbon atoms. And basically, the graphene is a crystalline allotrope of carbon, in other words, with two-dimensional properties. So the carbon atoms are packed density and regular atomic scale, like chicken wire something hexagonal pattern. The structure is hexagonal. Okay, so if you look at this scanning probe images, we are, if you look at here, there is no defect. So that's why my study was, when we studied the graphene, or without considering any defect, might be someone can be interested in who, what is the defect. Right now I'm giving one hint. We are working on the hexagonal boron nitride creating defect. The hexagonal boron nitride monolayer, it is a high band gap insulator. The band gap is around 7-8 electron volt. It has no role. Whereas the where is this a graphene band gap is 0? Why then will use hexagonal boron nitride? Yes, some cases it is required. If it is has really vacancy, it can reduce the metal. We are working on that, and unfortunately, that article was rejected by Nature and Nature Nanotechnology. We are working on that to submit again some Nature article, and we'll see how it will work. That how the defects can reduce transition metals, reduce noble metals like platinum, like gold. Such kind of research we have already done, and we found the kinetic barrier also. So what happened after the development of this a novel work is called graphene? I said it was exponentially developed this kind of graphene physics, graphene material, which is called a Nobel Prize when they gave in 2010. It was around 2009 that the why they gave the Nobel Prize is called groundbreaking experiment regarding the two-dimensional material graphene. So just 10 years back, this graphene came to the market as a potential, but in 2000 actually 4, after developing slowly 2D material is coming. But right now, if you open any journal, any research, probably all of many of us are working on the 2D, 2D graphene, 2D material for battery, these, that, many things. So another one of the material is coming is called silicens. I also work on that one. Silicon has, so the 2D silicon shows this kind of mechanical behavior. So this paper is under review, and we are working on that how the silicon will work for thermosaline material. Then we did also for borofin, but borofin right now I'm not working. Apart from that, many of us, for example, our one student Banti and I was also working on transitional metal oxide. In terms of it is 3D, it's called perovskite material. He's working on that. The mixing probably in some future will work on together mixing. Okay, and some of us and myself is working on alkali ion battery. Okay, this is the all other battery, lithium, sodium. Probably Akash will work on lithium, sodium, and Vikas also will work on transition metal oxide, transition metal dioxide, and also battery purposes. And phosphorine, we are thinking to work on that. So this is the just development of the graphene we are opening in that. But if you open some journal, you will get many articles on that. Hmm. So, so the graphene yesterday I was discussing what is the Dirac cone. Probably I do not need to repeat again since yesterday I described what is called graphene. But graphene shows the semimetallic behavior and Dirac cone in its linear band structure. So these kind of semimetallic behavior, Dirac cone properties can be explained by the density functions theory. Okay. So who are familiar with the 2D kind of material, they know very well Dirac cone, which represents linear energy dispersion at Fermi level, which gives graphene mass late fermions, which leadings to the various quantum Hall effects, which is ultra thin, ultra greater mobility, and many others novel phenomena and properties. Dirac cones are surfaces that describe the unusual electronic properties, and especially for the like graphene, like topological insulator. Some cases we found some organic material also shows a Dirac cone. So Dirac cone has lot of phenomena in physics, especially topological insulators, and that case is when we have that material at particular temperature, it will show zero and zero band gap. And exactly the cone. In that cases, what will happen? In that cases, the electron mass is basically effective mass of the electron in this case is in this region would be zero. So electron can freely move here to there. And there are many carbon nanotubes, the carbon nanotube. We will see some today, sometime, that how the carbon nanotube works. For that, let's the work what I did using density functions theory, which I think we are the probably first or second in the world. First, we will apply the density functions theory, especially hybrid density functions theory with three-leaf method using our new code. And I was working on the developer group who developed that kind of such kind of hybrid density functional, which is implemented in their code crystal. And if you look at the probably Bhav is not still now using this density functional. They are using GGA. GGA means generalized gradient approximation, LDA, such kind of method in their program. But in our program, we implemented with 3D. If you look at the method quality compared to LDA, GGA, density functional theory, basically any kind of density functional theory which have very better correlation parameter, better exchange parameter. Today we are discuss exchange parameter, correlation parameter, much better than LDA. Instead of considering homogeneous electron gas, basically material is not a gas, right? It is a solid. Okay, solid to be 3D structure is there. These are unit cell I showed many times, probably will be very important for us. Let's say this is the 2D 2D bilayer graphene structure. And now what problem is that when you stack the graphene monolayer, graphene one upon, there are two ways. If you look at, this is the graphene exactly parallel, and in such a way that each, if you look at this atom and this atom in the aligned particular way, it is called A stack. Mean what? The top of the second layer exactly the bottom of the second layer. It is called A stack bilayer graphene. In that cases, we found like exactly graphene has same kind of symmetry, P6 hexagonal symmetry, hexagonal structure, looks like very good. And the lattice costs are roughly 2.545 angstrom using our density function theory. We compared that it is very good for consistent with the experimental data. And we also plotted the band structure MK gamma M direction, missing the M here, MK gamma M direction. We found exactly the K point. Because of two graphene, there are two Dirac points, but it is not a cone. It is Dirac point, we give the name, because if we plot the different color, that would be better. I didn't do the near future, of course I will do. It is not forming the cone exactly at the Fermi level. They are shifted either down or top. Okay, so this is the way they have actually. That's why what we observe here, similar way, that there is no basically there is no basically no electron density, almost zero electron density, and it is just based like a very small band gap semiconductor. Similar way we plotted the total density of states. The total density of also so is like this, and which is followed the similar way what was I explaining for the graphene. This is the PZ. PZ is the G subcell, means PZ the Z component of that. So PZ, PX, PY, PZ, and PZ is coming from the P of the carbon, so it's instead of carbon. So you may imagine that when we are defining such kind of big structure, we need to define only two atoms in one unit cell. So it would be easy for us to optimize this crystal structure, or sorry, 2D layer structure. If you look at, it's a very big structure, but theoretically we need only two atoms and the symmetry. So that is the beauty of our program using the symmetry. In Vast, we cannot use this such kind of symmetry. In Vast, we have to consider each and every atoms in the unit cell. But I'm happy to tell you that we do not need such kind of each and everything, every atoms. But here, when we impose the symmetry, automatically it will count the rest of the atom which are coming from the symmetry. So our intention will be when we will develop some material, we must have to have the symmetry. If we don't have the symmetry, then computationally it will take long time and costly. When we will intercalate, we have to find out the symmetry. Very good. So in the second cases, we are giving the name is called AB stack bilayer graphene. So in that cases, what happened? A equal to B almost like same. What happened if you look at the white layer and another is called brown layer of carbon? They are parallel but in a slanting position. Means if you look at this, if you just slant little bit, this carbon will come at the center of this center of probably centroid, so center of this ring here, like that way. It's a slanting position. In that case, its symmetry is going to reduce. Initially it was p6 it is kind p minus trigonal symmetry, hexagonal to trigonal, and it has almost equal the lattice constant. It is called AB stacked bilayer graphene. And theoretically, when we studied, we found that a stacked graphene is the most stable because the energy value is more negative than this. And we similar way we have observed. Look at the band structure, how it looks like. Yes, bands are crossing up to that Fermi level, but occupied states are almost zero. There is no occupied electrons. Electron density is zero, and it has some gap also. It is roughly from the band gap, from band structure. You can sometimes cannot actually explain properly there is a gap or not, because some cases the bands are touching but there is no electron. That's why we have to calculate the total density of states. So in that case, we observe that it has a small gap, roughly 0.2 electron or 0.5 electron volt, because there is no occupied electron. Probably the gap is coming from here to here, and we found that the semiconductor behavior, semiconducting behavior, and the rest of the thing means total density of state followed by the similar way by PZ subcell, not the other part. Py some cases is coming is very negligible, but PZ is the most contributing component in the total density of states. So we have already learned the first figure, that's why I don't want to disturb. But now what we understand that A stack bilayer is a zero band gap semiconductor. Why is some semiconductor? Because the band gap is zero, and the band gap is zero, but the occupied electrons are less. Okay, that's why it's a zero band gap semiconductor. Less occupation of that kind of thing. So then what we did, we have intercalated vanadium atom. Okay. So vanadium atom, how we are intercalated vanadium atom? We took one concept. We are trying to intercalate such kind of atom between we have two layers. One ring we can consider here, one ring considered here. At the center of two rings we put the vanadium. So one vanadium atom for one unit cell we have considered as a 2D material. Then the material is called PLG1B, which will have a very good application for spintronics. And if we plot the band structure again, we'll see that there is a Dirac cone. But other point is that these bands, some bands is crossing to here, it might have some density. Yes. So we found the Dirac material which have the higher actually lattice constant compared to the piston, or almost more than double, and we'll see, or close to double, and the symmetry is the same. Okay, symmetry is the same, and the spin of this kind of electrons either up or down, means when if you look at the vanadium, it has 3 electron in D subcell. So in that electron either up or down, doesn't matter. We'll found that this is a Dirac material, it has a Dirac cone. Then what we did exactly in some similar way when we added the vanadium. In vanadium cases, we have to calculate the SPDF electronic subcell contribution. Then we found electronics orbital contribution. When we have plotted the D also, what we observed that DYZ is coupled with the PZ of the PZ electrons of the carbon. So that way we found the Dirac cone. But interesting thing is that there is a Dirac cone, excellent work, but the density of state is huge, not zero. What we observe for graphene, if we look at the graphene here, the total density of, probably I was showing in some slide, total density was zero. Okay, but in that cases when we have developed this Dirac material, Dirac cone is there, is a 2D Dirac material. For the first time we found theoretically it has a Dirac cone, but the density of state is not zero. That's why it would be useful for the spin trap devices. So BLG in bilayer graphene A stack is a semiconductor, but 2D material, whatever we have developed BLG with 1V, then what will happen? The Dirac cone is there, but the density of but the total density of state is not zero, and it's quite large density of is appearing because of the D subcell contribution of the D orbital contribution of the vanadium. Fine. Then the question will come from the audience, I expect. Instead of one, if we use two vanadium atom in one cell, then this study. But before going to that, we have to must know the electronic configuration of the vanadium. So vanadium atomic number, 23. So first one is 2s, 3s, 4s, like that. In 3D cell, we'll see three unpaired electrons are there, like this. This is called unpaired electron. In other cases, we'll see according to Hund's principle, electrons are, like this way, one spin up, one spin down, like that way from the pair. Okay, an unpaired electron is only observed in 3D subcell. Okay, so now let's say we have two vanadium atoms. That's why I put two atoms. Similar way per unit cell. In that cases, the structure is going to totally break. Okay, so we are considering all the spin, whatever I was showing, all the spin up, 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 up. Okay, so that's why I say spin up is called ferromagnetic alignment. From here, the source of magnetism will come later on. We work on, but the symmetry, when we added it, second number two, vanadium, the symmetry is going to break. So symmetry is going to be, the property is going to change. So what happened? The lattice constant is going to around 8.6 for A, and for B around 5. That's why the symmetry is going to Cm2. When symmetry is going to reduce from higher to lower. Okay. So P6mm is the most highest symmetry is coming down. P here is coming Cmm2 symmetry. And when we plotted the band structure in the same direction mk gamma m, we observed that bands are randomly overlapped. One valence band is going to this region and overlap with the conduction band. Similarly, this band also jumping. And we found that whatever calculation we did, the total density of states, individual electron density of states, each and every cases when we calculated SPDA, PX, PY, PG, and DX, whatever we observed that the properties is coming from the d electrons, the d electron of the vanadium, and it is a material conductor. Very good. Hopefully now I am able to show some interesting data. If we do the anti-ferromagnetic alignment, one spin up, one spin up, one spin down, same material. Then what we did, we control the spin in such a way total spin of the system is 0. It is called low spin, and it is called high spin when we have all the spin up, total spin is 6. So if we have the low spin, very interesting property observed. Although metals are there, what happens if you look at the bands? There is a gap. There is a gap here to here. There is small gap. Okay. So what we observe, the bands, this is the Fermi level, the valence band below the Fermi level, and conduction band above the Fermi level. They are not crossing each other. So basically, it's not crossing the Fermi level. What we observe, there is a small gap. It, let's say, around 0.2 or 0.3, whatever indirect band gap we observe. We also calculated the p orbital, d orbital of vanadium, p orbital of carbon. In that every cases we observe that occupied states are there fine, but density of states at the Fermi level definitely 0, and there is a gap. The gap is called some of the order of, let's say, volt or millivolt order. What we observe? We observe that if we regulate the spin, or we can control the spin in that such kind of intercalation process, we can get the semiconductor behavior of such kind of material. In past, probably the metal means one valence and always a conductor. It's not like that. Then we extended our work in the same periodic table, same column. Instead of vanadium, first we use niobium. Okay, let's to investigate why the Dirac cone is there. That is the question is coming. So what we did, if we use the niobium in per unit cell 1, it has the same symmetry and niobium color. Instead of red, I use probably I think like like green white something, and we see that the Dirac cone has moved from here to here, and it's going to behave like a metal, and Dirac point shifted around almost 1 electron volt. And we went to the next element in the same column. It's called tantalum. Tantalum I highlighted by some kind of yellow color. In such cases, symmetry is the same, and but Dirac point again is moving. Dirac point is moving again from more far compared to niobium. Okay, and we also calculated the total density of state we observed. In that case, the experiment they can observe only PL spectra. We can compare the XFS data. So we observed that around almost 1.7, 1.8 electron volt Dirac point move. Basically, what we observe, a Dirac cone does not exist in both these cases, BLG1 and BLG1 TA. But the band crossing point still exists, which is Dirac point still there, but The point is Dirac cone is missing. Okay. So then what is the reason? What is the reason behind that? People will ask, reviewer will ask, why you didn't see? So basically it is my comparison. Okay, look at that Dirac cone. Sorry to just interrupt here again. Vanadium, when we have intercalated BLGV, fine, it has a Dirac cone at the Fermi level. Yep. If you look at number figure B, when we are summarizing this comparison band structure, when niobium, the band point means band crossing point, Dirac point has moved whatever the circuit highlighted around 1 volt, and it is 1.4 electron volt when we have intercalated this. What happened? When the size of the atoms which are intercalating, the Dirac point is randomly moving, which is shifted up with respect to the Fermi level, and Dirac point, of course, the Dirac question is still there. So this kind of work we published in 2018 in Journal of Chemical Physics, and one is Journal of Physical Chemistry C. And we see that what is the reason behind that? Why the BLG1B has Dirac cone? Why not other? So my question is, when we have the BLG1B structure, I remove the BLG part, I put only material layer. This is the vanadium layer. In that cases, when we have plotted the material single layer, we plotted the band structure. Okay. So band structure only for the material, only for vanadium layer, it looks like that. High band gap. But when only BLG1B structure, BLG removed in these cases, the metal removed, the same geometry is there, we plotted the band structure. You will see that here is the Dirac cone. Okay. So what happened when the combine this thing, the important point will come, the symmetry and structure, geometry with the spin. What happened? The spin, symmetry, and electronic structure and geometry will affect to control the Dirac cone in this point. That's why we observe the Dirac cone. Okay. Then what we did, instead of 2D calculation, we continued our calculation in 3D. This is the 2D structure. This is the 3D structure. This is called top side view. These are the top view. So when it is a 3D structure, not is going to close only single layer. It will have many layers. Okay. This is the same multi-layer structure for the rest of the transition metal, including vanadium. So we found that not only vanadium, we continued all first row transition metal element except vanadium, no one shows this Dirac cone. Okay, and this is the layer I highlighted by parallelogram, which is the hexagonal structure. This is the unit cell when we have considered. Here is the unit cell. This is the 3D unit cell we have defined for the crystal structure calculation. Okay, and this is the summary we did. Okay, these are the papers we already published in 2018. Two papers. One is Journal of Physical Chemistry C, which is the famous for material scientists, material who are working on that area of faculty member. They know how this is the journals are prestigious. So hopefully I was able to explain you how the density functions theory. Look at, in these cases I didn't do any theory development. Getting the theory, we explore such kind of band structure and density of state and the properties of the material. Okay, so this is the way. Give me 1 minute rest, then we work. I will continue from here.